Assalamualaikum and selamat sejahtera. My name is Muhammad Firdaus Zamzuri. My student ID is 2024270696 and together with my friends or my members, Clarus Esteban Ignatius and also Syaiful Sharizan bin Sharifuddin. So today in this video, we will spend our time talking about topic that we chose as the nuclear reactor. A nuclear reactor is a system designed to produce energy through a controlled nuclear reaction, mainly through the process of nuclear fission. In a nuclear reactor, nucleus of heavy elements such as uranium-235 isotopes, also can be written as the symbol of U-235, will be split to release a large amount of heat energy. This heat energy is transferred to a coolant system, which is used to generate steam that drives turbines to produce electricity. Nuclear reactors are an important energy technology because they can generate large amounts of reliable energy while producing low carbon emission. What is the main reason we choose nuclear reactor as this video's main topic? So the first reason is because we want to investigate the real-world application of the nuclear reactor. Next, we want to explore possible career involving nuclear reactor. Then we also want to understand how the nuclear energy is converted into electricity inside the nuclear reactor. Then we also want to study the components and also the functions of each components of the nuclear reactor. And last one, we want to understand the process of nuclear fission that occur inside a nuclear reactor.
Next, let's look at our methodology. We followed a simple 6-step process for our research. First, we select the nuclear reactor based on our interest in modern physics. Then we reviewed our lecture notes and identified key topics like reactor definitions and future improvements. To expand on this, we gathered information from reliable websites and used AI tools like ChatGPT to simplify the content. Finally, we organized everything and put it right here into these presentation slides.
Even though this video was finally produced, we have experienced some challenges while researching for this topic of nuclear reactor. The first challenge is most information we searched for was highly technical and difficult to understand. And the second one is different websites sometimes provided us with information with different level of details. So the solutions we did is we referred to the official organization such as IAEA, or it stands for International Atomic Energy Agency, and also WNA, or also can be called as World Nuclear Association. And the last one, we compared multiple reliable sources to simplify the information for better understanding. We already know what is actually nuclear reactor, but how does it work in the real world? So when a uranium-235, or also can be written as the symbol of U-235, is struck by a high energy neutron, it will undergo a process that we call in physics as nuclear fission, in which the nucleus will be split into two smaller nuclei. This reaction will release a large amount of heat energy, along with additional neutrons, which will continue the controlled reaction chain inside the reactor core. The heat produced is then transferred to water flowing through the coolant system, converting it into high pressure steam. The steam flows through the turbine, causing it to rotate at high velocity or high speed. The rotating turbine drives a generator, where electromagnetic induction will convert the mechanical energy into electrical energy. The electricity generated is then transmitted through the power grid to supply home, industries, and other consumers, such university, schools, and so on. Now, what is nuclear fission in physics? Nuclear fission is referring to a nuclear reaction in which the nucleus of a heavy atom such as uranium-235 is struck by a neutron and splits into two smaller nuclei, that called as fission products. During this process, a large amount of heat energy, additional neutrons and also gamma radiation are released. The newly released neutrons can strike other uranium-235 nuclei, causing them to undergo fission as well. This creates a chain reaction that is carefully controlled inside the reactor core using control rods and other safety systems.
Now we're talking about function of each component in nuclear reactor. The first one is nuclear fuel. Fissile uranium pellets that split during chain reaction to produce thermal heat. Second one is neutron moderator. Water or graphite that slow down fast neutrons to safely sustain active fission. Third one is control rods. Cadmium or boron assemblies that absorb neutrons to speed up or halt the reaction. The fourth one is core coolant. Liquid water or gas circulating around the core to capture and transfer generated heat. The fifth one is pressure vessel, heavy steel chamber housing the active reactor core, coolant flow and moderator. Next is steam generator, a heat exchanger converting secondary water into high pressure steam for turbines. And lastly is containment structure, a thick concrete and steel outer dome preventing any environmental escape of radioactive materials. Now we're talking about how nuclear reactor is applicable in daily life. First is electricity and power grid. Fission reaction inside commercial reactor supplies over 10% global electricity. This serves as vital zero-emission baseload energy source, keeping urban power grid stable, active and carbon-free 24/7. Next is submarines and propulsion. Compact naval reactor power nuclear submarines, letting them run submerged for months and sail for over 20 years without refueling. This provides unrivaled deep-sea research, tactical defense and cargo operation. Next is nuclear medicine and scans. Reactor produce essential medical radioisotope like technetium-99m. These compounds are used globally across thousands of hospitals to perform precise SPECT or PET diagnostic imaging and targeted cancer therapies daily. Last is safety tech and gauging. The reactor generates americium-241, a critical isotope powering a residential ionization smoke detector to save lives daily. Additionally, industrial nuclear gauge ensures structural non-destructive testing of construction material. Now, we're talking about advancement on nuclear reactor. The first one is small modular reactor (SMRS). These are fractionally sized reactors built entirely in factories and shipped to location pre-assembled. They drastically cut construction costs and can power smaller grid systems or remote areas. Second is passive safety system. Generation 6 modern reactor use physics gravity, natural convection and circulation, and expansion-driven shutdown instead of electrical water pumps. So, if power completely fails, the physics of the system naturally cools the core to prevent a meltdown. Third is alternative coolant, that is molten salt and liquid metal. Instead of using high-pressure water, which can flash into explosive hydrogen gas during an accident, newer designs use molten salt or liquid sodium. They operate at normal atmospheric pressure, virtually eliminating explosion risk. And the last one is the horizon of nuclear fusion. While current commercial plants rely on fission, splitting atom, massive global projects are inching closer to fusion, smashing atoms together like the sun. Fusion promises limitless clean energy with zero long-lived radioactive waste. Now, we move forward to the controversies that associated to nuclear reactor. The first one is high-level radioactive waste. Spent nuclear fuel remains hazardous for tens of thousands of years, while solutions like deep geological repositories such as Finland on-Kalo repository exist. Finding permanent underground storage sites faces massive political and local resistance. The second one is the shadow of historical disaster. public perception remains deeply scared by high-profile disasters like Chernobyl and Fukushima Daiichi, even though modern engineering prevents these specific failure loops. Public anxiety about worst-case meltdown remains incredibly high. The third one is weapon proliferation risk. The enrichment technologies used to process uranium for civilian nuclear fuel are fundamentally similar to those required to build nuclear weapons. Expanding global nuclear energy infrastructure creates tight regulatory challenges regarding military security. And the last one is economic barriers and project delays. Project routinely suffer from multi-billions dollar budget overruns and take over a decade to complete, making them less financially attractive than too fast to build solar or wind farms.
Now let's look at the career paths available in this field. On the operation side, reactor operators directly handle the plant system, while neutronics engineer design the reactor cores. For safety, health physicists protects personnel from radiation, and regulatory inspectors enforce strict legal compliance. We also have medical physicists who use this technology for cancer treatments and decommissioning engineers who safely dismantle shutdown reactors and manage waste. There's a huge variety of roles depending on your focus. To excel in these careers, you need highly specific technical skills. First, computational neutronics is vital for simulating core life cycles, while thermal hydraulic designs ensures safe heat removal. You also need to understand material science to see how intense radiation degrades metals over time. On the safety front, mastering criticality control helps prevent accidental chain reactions, while shielding and dosimetry helps design physical barriers to protect people. Finally, knowing regulatory compliance is essential for passing safety audits. Continuous learning is crucial because the industry is rapidly changing. We are currently shifting towards Generation 4 design and small modular reactors, and increasingly using AI-driven tools for predictive maintenance. Cultivating a strict safety culture minimizes human error, while interdisciplinary synergy helps connect nuclear engineering with cybersecurity. Ultimately, staying updated allows us to preserve legacy knowledge so the next generation can step into senior roles smoothly. Lastly, let's look at the challenges and solutions. Regulatory bottlenecks and high startup costs can be overcome by using pre-licensed, factory-assembled modular reactors. To handle public stigma, we need transparent, science-based community engagements. For spent fuel disposal, we should promote breeder reactors that recycle waste. Finally, we must protect against cybersecurity threats using strict air gap networks and tackle workforce deficit by partnering with universities for targeted scholarships.